The hollow concrete block functions as a highly precise, mathematically proportioned structural system designed to handle severe compressive loads. Its performance and physical tolerances are governed by the engineering parameters found in Indian Standard 2185. Structural integrity begins with the face shells. These outer vertical plates serve as the primary load-bearing paths that transfer weight through the wall. Connecting and stabilizing these face shells are the webs. These internal transverse walls are required to prevent the face shells from buckling outward under structural stress. While engineering drawings often list nominal dimensions, such as a 400 mm length, the actual block is cast 10 mm shorter in both length and depth. This precise reduction is engineered to perfectly accommodate the thickness of the mortar joint. To classify as a hollow unit, the combined volume of the face shells and webs must constitute between 50 and 75% of the block's total calculated volume. The geometry and material volume of each single unit directly dictate the load-bearing strategy for the entire wall. This table from IS 2185 shows how block grading is determined by a rigid material density matrix. Grade A hollow blocks require a minimum density of 1,500 kilograms per cubic meter. They are engineered for heavy load-bearing construction, with minimum average compressive strengths reaching 15 newtons per square millimeter. Grade B hollow blocks operate under lower density parameters, between 1,100 and 1,500 kilograms per cubic meter. These are restricted to moderate load-bearing applications. Grade C units are strictly solid concrete blocks. These require the highest minimum density, exceeding 1,800 kilograms per cubic meter, to achieve their structural capacity. The minimum average compressive strength a unit can support scales proportionally with these density thresholds. This grading matrix forces structural engineers to explicitly match the unit density to the specific calculated load of the building. Traditional bricklayers often soak building units in water before laying them. When working with concrete blocks, this habit is a fatal error. While porous clay bricks must be soaked to prevent sucking hydration out of the mortar, concrete chemistry behaves differently. Concrete blocks are dimensionally unstable when exposed to water. If a block is soaked, it will swell, and then, as it cures inside the finished wall, it shrinks, pulling the surrounding mortar apart. Because of this volumetric instability, the IS 2572 code mandates concrete units be laid perfectly dry. The code limits this to a maximum drying shrinkage of 0.06% and moisture movement of 0.09%. Adding unnecessary water magnifies these stresses. Trapped moisture from pre-wetting guarantees volumetric contraction, effectively tearing the masonry system apart. Using a stronger mortar mix often creates a weaker wall system. A highly rigid mortar acts as an unyielding constraint. When the blocks undergo minor temperature or moisture expansions, the rigid mortar forces that stress into the units, causing structural fractures. IS 2572 mandates an engineered solution using composite mortar mixes designed to remain relatively weaker than the blocks. Adding precise proportions of hydrated lime to cement and sand increases plasticity. This creates a yielding buffer that safely absorbs micro-movements across the wall. For heavy load-bearing construction, full mortar bedding spreads the mix evenly across face shells and internal webs. For non-load-bearing walls, face shell bedding is utilized. Mortar is applied only to the outer shells, leaving internal webs bare to arrest capillary water seepage. In concrete masonry, mortar serves as a flexible, localized shock absorber for the entire wall assembly. As mortar hardens, it naturally shrinks and pulls away from the block edges, creating weak points. To combat this, the code requires builders to use a jointing tool to compress the mortar after it has stiffened, creating a weather-tight seal against the unit. This compaction is critical around doors and window openings, which represent the most vulnerable points in the masonry. Openings act as severe stress multipliers. The dead weight of the wall above a void attempts to shear downward, requiring localized structural reinforcement. IS code requires adjacent hollow cores flanking an opening to be entirely filled with a dense 1 to 3 to 6 concrete grout mix. High-strength 10 mm deformed steel bars must be embedded within these grouted cores to capture and transfer shear loads to the foundation. Without proper grouting and steel reinforcement, these framed openings will become ground zero for structural cracking. At the macro level, we must manage the behavior of massive, continuous wall assemblies that may exceed 30 meters in length. Even with dry blocks and yielding mortar, thermal expansion and moisture movement across a wall of this scale are unavoidable. Control joints are engineered to safely absorb this movement. These unbonded vertical gaps allow discrete wall sections to expand and contract independently. The code dictates that in free, unsupported walls, these joints must be placed every 8 to 10 meters. Engineers cannot stop volumetric movement. They can only dictate exactly where and how it happens. A code-compliant concrete block wall is a calibrated system of dry units, yielding mortar, and calculated expansion gaps designed to survive its own internal forces.